Good morning, ladies and gentlemen. In my series of lecture on flight performance and planning, I am going to cover takeoff flight path and its different segments. At the end of this class, you will be able to answer many questions, including the net flight path clears all the obstacles by how many feet. While considering the obstacle clearance, the gradient under consideration is whether a gradient or a ground gradient. What are the minimum climb gradients during second and fourth segment? And what do you understand by minimum acceleration altitude and the maximum acceleration altitude and its significance? What is the maximum time up to which you should be able to reach VFTO speeds, or in some other aircrafts, green dot speeds, and come to a clean configuration. So now let us continue the class. As we discussed earlier, the purpose of an aircraft flying from one place to another place is to carry certain amount of load. But however, the primary requirement is that with this load or gross weight of the aircraft in the event of engine failure should be able to clear all the obstacle by the required regulatory margin. So in my previous lecture, we have talked about the first phase of the flight, that is takeoff, which commences at brake release and finishes at V2 at 35 feet. So in this lecture, we will continue from that portion, that in the event of an engine failure, during the takeoff at a V engine failure speeds and at a V1, you decided that you will continue the takeoff. So therefore, you rotated at VR and the aircraft lifts out at VLOF and reaches V2 at 35 feet at the end of the takeoff distance available. The portion of the flight starting from V2 at 35 feet, that is at screen height, till the time you reach a minimum altitude of 1,500 feet or en route config, whichever is higher, is known as the takeoff flight path. This takeoff flight path can be divided into 4 segments. As discussed, the first segment will start at the time when you reach V2 at 35 feet screen height at the end of takeoff distance available. At this moment, the aircraft is going to take the landing gear or undercarriage up. The moment the landing gear is fully retracted, that is the time when the transition from first segment to second segment happens. During the second segment, you will be climbing with a V2 speed to the minimum acceleration altitude of 400 feet. The moment you reach the minimum acceleration altitude, the third segment will commence. The third segment will commence from the minimum acceleration altitude till the time the aircraft comes to a clean configuration at VFTO speed, that is the final takeoff speed, or in some aircraft it is also known as the green dot speed. The maximum time at which you have to reach this VFTO speed on a clean config is 10 minutes on takeoff thrust or takeoff power. Once the takeoff power has been reduced to MCT, then the aircraft will start climbing up to a minimum of 1500 feet above the ground or en route config, whichever is higher. So these are the different segments, and we will see some more characteristics of these different segments. As we said that the first segment commences at a V2 35 feet and it will end when the landing gear is fully retracted. During this stage, the power or the thrust rating of the aircraft will be a takeoff power or a takeoff thrust. And the aircraft is on the takeoff config and you are climbing with a V2 speed and the gradient of climb is positive. Once the landing gear is fully retracted, the second segment starts And during this segment, the power or the thrust rating will be still at takeoff power or takeoff thrust. The aircraft is still in takeoff config, and you are climbing with a speed of V2 with a minimum gradient of 2.4% for twin engine aircraft and 3% for 4-engine aircraft. Once you reach the minimum acceleration altitude or the height, the third segment will commence. During this segment, the power or thrust is still at takeoff power or takeoff thrust. The aircraft is in a process of cleaning up. You are going to be increasing the speed from V2 to the final takeoff speed, that is VFTO. As I said earlier, in some of the aircraft it is also known as the green dot speed. During this period, you will be cleaning up the flaps in stages. So therefore, the aircraft capability to climb can now be converted into the capability of the acceleration. After having reached 10 minutes of maximum time up to which you can maintain the takeoff thrust or the takeoff power, and after the aircraft has come to the speed of VFTO and the clean config, the power or thrust will be reduced now to MCT, and the aircraft will start climbing in a clean config with a speed of VFTO, and the minimum regulatory climb requirement for a twin engine aircraft is 1.2%, and for 4-engine aircraft it is 1.7%. The climb gradient is shown in the climb path is shown in the yellow line. In this yellow line, it is, as I have depicted, to be more critical. It is not a straight line here. It is not a straight line here, except the third segment, which is an acceleration segment. Why it is not a straight line is, as you start climbing higher and higher, the power or thrust output of the engine is slowly reducing. So therefore, in the beginning of the climb segment, the climb gradient is going to be higher. As you keep increasing the altitude, the power output or the thrust output of the engine is slowly reducing. So therefore, you will have a lower climb gradient. So therefore, in this picture, the line is a curved line. But during this period, in all this segment, the minimum climb gradient you must achieve is as given. Okay, positive gradient 2.4 or 3%, depending upon whether it is a twin engine aircraft or 4-engine aircraft. Here it is not climbing, so therefore the power output or the thrust output remains the same. So therefore it is a straight line. And in the last segment, as power output or the thrust output reducing, the curve is also bending. And the minimum gradient is 1.2 for twin engine, 1.7 for 4-engine aircraft. So this flight path under consideration is the gross flight path, which normally the aircraft should be able to follow it, and it is considered under still air. Why I said that normally the aircraft should be able to follow it is that because of the variation in the flying technique, piloting skills, and because of the variation in the atmospheric conditions, okay, the gross flight path may differ. Okay, so the gross flight path may differ. So in order to consider the obstacle clearance, this difference in the gross flight path, okay, because of flying technique or because of the environmental factors, needs to be catered in. So therefore, we need to define something known as the net flight path. In this diagram, I have depicted as a green line. So how this net flight path is derived is, net flight path is derived out of the gross flight path by reducing certain percentage. For a twin engine aircraft, the reduction is 0.8%. For 4-engine aircraft, the reduction is 1%. So after having reduced this gross flight path by the required margin, then I will get the net flight path. The requirement by the regulators is that the net flight path should be able to clear obstacle by a margin of 35 feet. So since after having given the margin, if this net flight path clears all the obstacle by 35 feet on any given day, if the aircraft is flying with minor variation from the gross flight path because of flying technique, because of the environmental factors, at all times my aircraft will always be able to clear all the obstacle by the required margin and the aircraft is considered safe. So as I said that while consideration of the gross flight path, the gradient which are under consideration is a still air gradient. While discussing the obstacle clearance margin, the clearance will be considered with the ground gradient after having considered the winds, because depending upon the winds, the gradient which the aircraft is going to maintain will vary. How will it vary? We will have a look. In this particular diagram, the first diagram shows the aircraft considering the still air maintaining a TAS of 120 knots. Let us assume that you are at the minimum acceleration height, that is at 400 feet, and with the obstacle here, the obstacle clearance margin required was 35 feet. So in this still air condition, how will we calculate the gradient? The gradient is nothing but the height gain divided by the ground distance travel multiplied by 100. So here it is a still air, the TAS will be equivalent to ground speed, so therefore the gradient will be 100 multiplied by 400. The ground speed, which when converted to feet per minute, that is 120 into 1060 will give me the in feet, and thereafter divided by 60 will give you feet per minute. So therefore my gradient is 3.289% in the still air. Now let's consider that the aircraft is having a tailwind of 10 knots. The height gain achieved still is 400 feet. However, because of the tailwind of 10 knots, my ground speed with a TAS of 120 will now become 130 knots of ground speed. So therefore, if we calculate the gradient, same formula, calculate the gradient, then my gradient remains 3.036%. The gradient now has been reduced as depicted in the particular diagram. When you are overhead this particular obstacle, the obstacle clearance margin is not able to achieve in case of a tailwind. But now in case of a headwind, let us consider similar headwind, that is headwind of 10 knots. Since I am having a headwind of 10 knots, my ground speed for the TAS of 120 knots will be 110 knots. So which when converted into gradient using the same principle becomes 3.588. So therefore by the time I reach the obstacle clearance criteria is much more than as compared with the tailwind. In this tailwind, the green diagram, the green triangle is after considering the tailwind. The red triangle is for the nil wind condition. Similarly, the blue triangle here is for the headwind and the red triangle here is for the still air condition. So therefore, in a headwind, your gradient is better as compared to the tailwind. So since in case of a headwind, I am having a good gradient. However, in order to be more conservative and take a little bit of safety margin under consideration, if you are having a headwind of 10 knots, the consideration for computation of those tables in the graphs will be only 50% of the headwind, that is 5 knots only. Since the tailwind is not helping us, I will consider to be more conservative a tailwind of 150%. That means to say that if you are having a tailwind of 10 knots, for computation of the graphs in the table, the tailwind under consideration will be 15 knots. Here, I am going to reiterate one thing. This consideration of 50% of the headwind or the 150% of the tailwind is done at the manufacturer level when they are preparing the graphs and the table for us, that is in the flight manuals. I repeat, this application of headwind of 50% and the 150% of tailwind is done by the manufacturer while preparing the graphs and the table for us. As far as the flight crew is concerned, I will be using the tower reported wind or the actual wind which is prevailing at that moment of time. So therefore, we have realize that for consideration of the obstacle clearance, the ground gradient is used and not the air gradient. And we also said that the net flight path under consideration should be able to clear all the obstacle by the required margin, that is 35 feet. Now let us talk more about the minimum acceleration height and the maximum acceleration height. The minimum acceleration height required by the regulator is 400 feet above the aerodrome level. However, if you have an obstacle at the takeoff flight path, in order to clear those obstacles by the regulatory margin of 35 feet, your minimum acceleration height needs to be increased. For example, if I have a hill which is high enough like this, so my flight path has to be above the one which is given in the red one in order to clear the obstacle by the required margin. But now, similarly, for the final segment also, we said that the minimum altitude at which we consider ending of the takeoff flight path is at 1500 feet. However, if you have an obstacle in this particular segment, okay, whose height is more than 1500 feet, then in order to clear the obstacle by the required margin, this 1500 feet also needs to be revised to a higher altitude. So therefore, when we say that the end of the fourth segment is at 1500 feet minimum, or the moment you reach the end route config, whichever is higher. What exactly is maximum acceleration height? In order to define this, I am going to take an example with an arbitrary figure. After getting airborne, it is mandatory for the aircraft to reach the minimum acceleration altitude and increase the speed. Okay, that is in order to ensure the obstacle clearance in the third segment. Consider that the time which is required to reach the minimum acceleration altitude, here in this case, follow my mouse here, it is 4 minutes. It will also approximately take 4 minutes in multiple aircraft. And at this point of time, I am supposed to increase my speed from the V2 speed to the final takeoff speed, that is VFTO or green dot speed. And let us assume that in order to increase the speed from V2 to the green dot speed, the time required is another 3 minutes. So now I have to end this segment at the end of 10 minutes, that is the maximum time up to which I can maintain the takeoff thrust. So out of these 10 minutes, I have utilized 4 minutes to climb up to the minimum acceleration altitude, and another 3 minutes I have to reserve, okay, in order to increase the speed from V2 to the green dot speed or the VFTO speed. So after having considered this 4 plus 3 minutes, that is 7 minutes, okay, I am still left with 3 minutes of time. In this 3 minutes of time which I have in my hand, the captain of the aircraft at that moment can consider or continue climbing. The maximum height or the altitude you can reach in this 4 plus 3, that is 7 minutes, is what we call it as a maximum acceleration altitude. Once we cross this maximum altitude, or after having reached this maximum acceleration altitude, I still have preserved that 3 minutes to increase the speed from V2 to the green dot speed or VFTO speed. So therefore, the moment I exceed or cross this maximum acceleration altitude and try to increase my speed, I do not have sufficient time, that is 3 minutes required left for me to increase the speed from V2 to the VFTO speed and come to a clean config and start climbing with a clean config. So therefore, this will compromise my further segment of climb. So therefore, one cannot burst or one cannot cross this maximum acceleration altitude. You have to level out at maximum acceleration altitude and increase the speed from V2 to the VFTO speed. Otherwise, you will not be able to bring the aircraft back to MCT before the end of 10 minutes, which is the maximum which is required. Now, whatever we have talked about was for a dry runway, operation on a dry runway. However, if you are operating on a wet or a contaminated runway, the regulators has permitted us to reduce the screen height from 35 feet to 15 height, and at the same time, in case of a reject takeoff, I can take the credit for the reversers. But since it is a continuation of the takeoff, okay, I will consider the reduction of the screen height. The gross flight path at the end of your takeoff distance available, okay, will be the one which is depicted in yellow color, and your aircraft will be 15 feet above the ground, that is the screen height of 15 feet. So therefore, in the initial part of your takeoff, for the close by the obstacle clearance required, obstacle clearance actual which you are going to have is slightly less than compared to that of a dry runway, which one needs to always keep it in mind. With this, I have finished today's lecture. If you have further questions or any clarifications, then you can send it onto the comment box. I will be happy to answer. With this, if you think that if this video is worth sharing, I request you to press the notification bell or subscribe it, and kindly do share with your friends so that they can also benefit from this class. Thank you, ladies and gentlemen. Have a nice day.